Chapter 6 The Analysis of a Complete Act of Thought. Object of Part 2. After a brief consideration in the first chapter of the nature of reflective thinking, we turned, in the second, to the need for its training. Then we took up the resources, the difficulties, and the aim of its training. The purpose of this discussion was to set before the student the general problem of the training of mind. The purport of the second part, upon which we are now entering, is giving a fuller statement of the nature and normal growth of thinking preparatory to considering in the concluding part the special problems that arise in connection with its education. In this chapter we shall make an analysis of the process of thinking into its steps or elementary constituents, basing the analysis upon descriptions of a number of extremely simple but genuine cases of reflective experience. A simple case of practical deliberation. 1. The other day, when I was downtown on 16th Street, a clock caught my eye. I saw that the hands pointed to 12:20. This suggested that I had an engagement at 124th Street at 1 o'clock. I reasoned that, as it had taken me an hour to come down on a surface car, I should probably be 20 minutes late if I returned the same way. I might save 20 minutes by a subway express. But was there a station near? If not, I might lose more than 20 minutes in looking for one. Then I thought of the elevated, and I saw there was such a line within 2 blocks. But where was the station? If it were several blocks above or below the street I was on, I should lose time instead of gaining it. My mind went back to the subway express as quicker than the elevated. Furthermore, I remembered that it went nearer than the elevated to the part of 124th Street I wished to reach, so that time would be saved at the end of the journey. I concluded in favor of the subway and reached my destination by 1 o'clock. A simple case of reflection upon an observation. 2. Projecting nearly horizontally from the upper deck of the ferry boat on which I daily crossed the river is a long white pole, bearing a gilded ball at its tip. It suggested a flagpole when I first saw it. Its color, shape, and gilded ball agreed with this idea, and these reasons seemed to justify me in this belief. But soon difficulties presented themselves. The pole was nearly horizontal, an unusual position for a flagpole. In the next place, there was no pulley, ring, or cord by which to attach a flag. Finally, there were elsewhere 2 vertical staffs from which flags were occasionally flown. It seemed probable that the pole was not there for flag flying. I then tried to imagine all possible purposes of such a pole, and to consider for which of these it was best suited. Possibly it was an ornament, but as all the ferry boats and even the tugboats carried like poles, this hypothesis was rejected. Possibly it was the terminal of a wireless telegraph, but the same considerations made this improbable. Besides, the more natural place for such a terminal would be the highest part of the boat, on top of the pilot house. Its purpose might be to point out the direction in which the boat is moving. In support of this conclusion, I discovered that the pole was lower than the pilot house, so that the steersman could easily see it. Moreover, the tip was enough higher than the base, so that, from the pilot's position, it must appear to project far out in front of the boat. Moreover, the pilot being near the front of the boat, he would need some such guide as to its direction. Tugboats would also need poles for such a purpose. This hypothesis was so much more probable than the others that I accepted it. I formed the conclusion that the pole was set up for the purpose of showing the pilot the direction in which the boat pointed, to enable him to steer correctly. A simple case of reflection involving experiment. 3. In washing tumblers in hot soap suds and placing them mouth downward on a plate, bubbles appeared on the outside of the mouth of the tumblers and then went inside. Why? The presence of bubbles suggests air, which I note must come from inside the tumbler. I see that the soapy water on the plate prevents escape of the air save as it may be caught in bubbles. But why should air leave the tumbler? There was no substance entering to force it out. It must have expanded. It expands by increase of heat or by decrease of pressure, or by both. Could the air have become heated after the tumbler was taken from the hot suds? Clearly not the air that was already entangled in the water. If heated air was the cause, cold air must have entered in transferring the tumblers from the suds to the plate. I test to see if this supposition is true by taking several more tumblers out. Some I shake so as to make sure of entrapping cold air in them. Some I take out holding mouth downward in order to prevent cold air from entering. Bubbles appear on the outside of every one of the former and on none of the latter. I must be right in my inference. Air from the outside must have been expanded by the heat of the tumbler, which explains the appearance of the bubbles on the outside. But why do they then go inside? Cold contracts. The tumbler cooled and also the air inside it. Tension was removed, and hence bubbles appeared inside. To be sure of this, I test by placing a cup of ice on the tumbler while the bubbles are still forming outside. They soon reverse. The three cases form a series. These three cases have been purposely selected so as to form a series from the more rudimentary to more complicated cases of reflection. The first illustrates the kind of thinking done by everyone during the day's business, in which neither the data nor the ways of dealing with them take one outside the limits of everyday experience. The last furnishes a case in which neither problem nor mode of solution would have been likely to occur except to one with some prior scientific training. The second case forms a natural transition. Its materials lie well within the bounds of everyday, unspecialized experience, but the problem, instead of being directly involved in the person's business, arises indirectly out of his activity, and accordingly appeals to a somewhat theoretic and impartial interest. We shall deal, in a later chapter, with the evolution of abstract thinking out of that which is relatively practical and direct. Here we are concerned only with the common elements found in all the types. 5 distinct steps in reflection. Upon examination, each instance reveals, more or less clearly, 5 logically distinct steps. 1. A felt difficulty. 2. Its location and definition. 3. Suggestion of possible solution. 4. Development by reasoning of the bearings of the suggestion. 5. Further observation and experiment leading to its acceptance or rejection, that is, the conclusion of belief or disbelief. 1. The occurrence of a difficulty. A. In the lack of adaptation of means to end. 1. The first and second steps frequently fuse into one. The difficulty may be felt with sufficient definiteness as to set the mind at once speculating upon its probable solution, or an undefined uneasiness and shock may come first, leading only later to definite attempt to find out what is the matter. Whether the two steps are distinct or blended, there is the factor emphasized in our original account of reflection, viz., the perplexity or problem. In the first of the 3 cases cited, The difficulty resides in the conflict between conditions at hand and a desired and intended result, between an end and the means for reaching it. The purpose of keeping an engagement at a certain time and the existing hour taken in connection with the location are not congruous. The object of thinking is to introduce congruity between the two. The given conditions cannot themselves be altered. Time will not go backward, nor will the distance between 16th Street and 124th Street shorten itself. The problem is the discovery of intervening terms which, when inserted between the remoter end and the given means, will harmonize them with each other. B. In identifying the character of an object. In the second case, the difficulty experienced is the incompatibility of a suggested and, temporarily, accepted belief that the pole is a flagpole, with certain other facts. Suppose we symbolize the qualities that suggest flagpole by the letters A, B, C. Those that oppose this suggestion by the letters P, Q, R. There is, of course, nothing inconsistent in the qualities themselves, but in pulling the mind to different and incongruous conclusions they conflict, hence the problem. Here the object is the discovery of some object O, of which A, B, C, and P, Q, R may all be appropriate traits, just as, in our first case, it is to discover a course of action which will combine existing conditions and a remoter result in a single whole. The method of solution is also the same. Discovery of intermediate qualities, the position of the pilot house, of the pole, the need of an index to the boat's direction, symbolized by D, G, L, O, which bind together otherwise incompatible traits. C. In explaining an unexpected event. In the third case, an observer trained to the idea of natural laws or uniformities finds something odd or exceptional in the behavior of the bubbles. The problem is to reduce the apparent anomalies to instances of well-established laws. Here the method of solution is also to seek for intermediary terms which will connect, by regular linkage, the seemingly extraordinary movements of the bubbles with the conditions known to follow from processes supposed to be operative. 2. Definition of the difficulty. 2. As already noted, the first two steps, the feeling of a discrepancy or difficulty, and the acts of observation that serve to define the character of the difficulty, may, in a given instance, telescope together. In cases of striking novelty or unusual perplexity, the difficulty, however, is likely to present itself at first as a shock, as emotional disturbance, as a more or less vague feeling of the unexpected, of something queer, strange, funny, or disconcerting. In such instances, there are necessary observations deliberately calculated to bring to light just what is the trouble, or to make clear the specific character of the problem. In large measure, the existence or non-existence of this step makes the difference between reflection proper, or safeguarded critical inference, and uncontrolled thinking. Where sufficient pains to locate the difficulty are not taken, suggestions for its resolution must be more or less random. Imagine a doctor called in to prescribe for a patient. The patient tells him some things that are wrong. His experienced eye, at a glance, takes in other signs of a certain disease. But if he permits the suggestion of this special disease to take possession prematurely of his mind, to become an accepted conclusion, his scientific thinking is by that much cut short. A large part of his technique, as a skilled practitioner, is to prevent the acceptance of the first suggestions that arise, even, indeed, to postpone the occurrence of any definite suggestion till the trouble, the nature of the problem, has been thoroughly explored. In the case of a physician, this proceeding is known as diagnosis, but a similar inspection is required in every novel and complicated situation to prevent rushing to a conclusion. The essence of critical thinking is suspended judgment, and the essence of this suspense is inquiry to determine the nature of the problem before proceeding to attempts at its solution. This, more than any other thing, transforms mere inference into tested inference, suggested conclusions into proof. 3. Occurrence of a suggested explanation or possible solution. 3. The third factor is suggestion. The situation in which the perplexity occurs calls up something not present to the senses. The present location, the thought of subway or elevated train, the stick before the eyes, the idea of a flagpole, an ornament, an apparatus for wireless telegraphy, the soap bubbles, the law of expansion of bodies through heat and of their contraction through cold. A. Suggestion is the very heart of inference. It involves going from what is present to something absent. Hence, it is more or less speculative, adventurous. Since inference goes beyond what is actually present, it involves a leap, a jump, the propriety of which cannot be absolutely warranted in advance, no matter what precautions be taken. Its control is indirect, on the one hand, involving the formation of habits of mind which are at once enterprising and cautious, and on the other hand, involving the selection and arrangement of the particular facts upon perception of which suggestion issues. B. The suggested conclusion, so far as it is not accepted but only tentatively entertained, constitutes an idea. Synonyms for this are supposition, conjecture, guess, hypothesis, and, in elaborate cases, theory. Since suspended belief, or the postponement of a final conclusion pending further evidence, depends partly upon the presence of rival conjectures as to the best course to pursue or the probable explanation to favor, cultivation of a variety of alternative suggestions is an important factor in good thinking. 4. The rational elaboration of an idea. 4. The process of developing the bearings, or, as they are more technically termed, the implications, of any idea with respect to any problem is termed reasoning. As an idea is inferred from given facts, so reasoning sets out from an idea. The idea of elevated road is developed into the idea of difficulty of locating station, length of time occupied on the journey, distance of station at the other end from the place to be reached. In the second case, the implication of a flagpole is seen to be a vertical position, of a wireless apparatus, location on a high part of the ship, and, moreover, absence from every casual tugboat, while the idea of index to direction in which the boat moves, when developed, is found to cover all the details of the case. Reasoning has the same effect upon a suggested solution as more intimate and extensive observation has upon the original problem. Acceptance of the suggestion in its first form is prevented by looking into it more thoroughly. Conjectures that seem plausible at first sight are often found unfit or even absurd when their full consequences are traced out. Even when reasoning out the bearings of a supposition does not lead to rejection, it develops the idea into a form in which it is more opposite to the problem. Only when, for example, the conjecture that a pole was an index pole had been thought out into its bearings, could its particular applicability to the case in hand be judged. Suggestions at first seemingly remote and wild are frequently so transformed by being elaborated into what follows from them as to become apt and fruitful. The development of an idea through reasoning helps at least to supply the intervening or intermediate terms that link together into a consistent whole apparently discrepant extremes. 5. Corroboration of an idea and formation of a concluding belief. 5. The concluding and conclusive step is some kind of experimental corroboration or verification of the conjectural idea. Reasoning shows that if the idea be adopted, certain consequences follow. So far, the conclusion is hypothetical or conditional. If we look and find present all the conditions demanded by the theory, and if we find the characteristic traits called for by rival alternatives to be lacking, the tendency to believe, to accept, is almost irresistible. Sometimes direct observation furnishes corroboration, as in the case of the pole on the boat. In other cases, as in that of the bubbles, experiment is required. That is, conditions are deliberately arranged in accord with the requirements of an idea or hypothesis to see if the results theoretically indicated by the idea actually occur. If it is found that the experimental results agree with the theoretical or rationally deduced results, and if there is reason to believe that only the conditions in question would yield such results, the confirmation is so strong as to induce a conclusion, at least until contrary facts shall indicate the advisability of its revision. Observation exists at the beginning and again at the end of the process. At the beginning, to determine more definitely and precisely the nature of the difficulty to be dealt with. At the end, to test the value of some hypothetically entertained conclusion. Between those two termini of observation, we find the more distinctly mental aspects of the entire thought cycle. 1. Inference, the suggestion of an explanation or solution, and 2. Reasoning, the development of the bearings and implications of the suggestion. Reasoning requires some experimental observation to confirm it, while experiment can be economically and fruitfully conducted only on the basis of an idea that has been tentatively developed by reasoning. The trained mind, one that judges the extent of each step advisable in a given situation. The disciplined or logically trained mind, the aim of the educative process, is the mind able to judge how far each of these steps needs to be carried in any particular situation. No cast iron rules can be laid down. Each case has to be dealt with as it arises, on the basis of its importance and of the context in which it occurs. To take too much pains in one case is as foolish, as illogical, as to take too little in another. At one extreme, almost any conclusion that ensures prompt and unified action may be better than any long delayed conclusion, while at the other, decision may have to be postponed for a long period, perhaps for a lifetime. The trained mind is the one that best grasps the degree of observation, forming of ideas, reasoning, and experimental testing required in any special case, and that profits the most in future thinking by mistakes made in the past. What is important is that the mind should be sensitive to problems and skilled in methods of attack and solution. End of chapter 6. Chapter 7. Systemic Interference, Induction and Deduction. 1. The double movement of reflection. Back and forth between facts and meanings. The characteristic outcome of thinking we saw to be the organization of facts and conditions which, just as they stand, are isolated, fragmentary, and discrepant, the organization being effected through the introduction of connecting links or middle terms. The facts as they stand are the data, the raw material of reflection. Their lack of coherence perplexes and stimulates to reflection. There follows the suggestion of some meaning which, if it can be substantiated, will give a whole in which various fragmentary and seemingly incompatible data find their proper place. The meaning suggested supplies a mental platform, an intellectual point of view, from which to note and define the data more carefully, to seek for additional observations, and to institute experimentally changed conditions. Inductive and deductive. There is thus a double movement in all reflection, a movement from the given partial and confused data to a suggested comprehensive or inclusive entire situation, and back from this suggested whole, which as suggested is a meaning, an idea, to the particular facts, so as to connect these with one another and with additional facts to which the suggestion has directed attention. Roughly speaking, the first of these movements is inductive, the second deductive. A complete act of thought involves both. It involves, that is, a fruitful interaction of observed or recollected particular considerations and of inclusive and far-reaching general meanings. Hurry versus caution. This double movement to and from a meaning may occur, however, in a casual, uncritical way, or in a cautious and regulated manner. To think means, in any case, to bridge a gap in experience, to bind together facts or deeds otherwise isolated. But we may make only a hurried jump from one consideration to another, allowing our aversion to mental disquietude to override the gaps, or we may insist upon noting the road traveled in making connections. We may, in short, accept readily any suggestion that seems plausible, or we may hunt out additional factors, new difficulties, to see whether the suggested conclusion really ends the matter. The latter method involves definite formulation of the connecting links, the statement of a principle, or, in logical phrase, the use of a universal. If we thus formulate the whole situation, the original data are transformed into premises of reasoning. The final belief is a logical or rational conclusion, not a mere de facto termination. Continuity of relationship, the mark of the latter. The importance of connections binding isolated items into a coherent single whole is embodied in all the phrases that denote the relation of premises and conclusions to each other. 1. The premises are called grounds, foundations, bases, and are said to underlie, uphold, support the conclusion. 2. We descend from the premises to the conclusion, and ascend or mount in the opposite direction, as a river may be continuously traced from source to sea or vice versa. So the conclusion springs, flows, or is drawn from its premises. 3. The conclusion, as the word itself implies, closes, shuts in, locks up together the various factors stated in the premises. We say that the premises contain the conclusion, and that the conclusion contains the premises, thereby marking our sense of the inclusive and comprehensive unity in which the elements of reasoning are bound tightly together. Systematic inference, in short, means the recognition of definite relations of interdependence between considerations previously unorganized and disconnected, this recognition being brought about by the discovery and insertion of new facts and properties. Scientific induction and deduction. This more systematic thinking is, however, like the cruder forms in its double movement, the movement toward the suggestion or hypothesis, and the movement back to the facts. The difference is in the greater conscious care with which each phase of the process is performed. The conditions under which suggestions are allowed to spring up and develop are regulated. Hasty acceptance of any idea that is plausible, that seems to solve the difficulty, is changed into a conditional acceptance pending further inquiry. The idea is accepted as a working hypothesis, as something to guide investigation and bring to light new facts, not as a final conclusion. When pains are taken to make each aspect of the movement as accurate as possible, the movement toward building up of the idea is known as inductive discovery, induction for short; the movement toward developing, applying, and testing as deductive proof, deduction for short. Particular and universal. While induction moves from fragmentary details or particulars to a connected view of a situation, universal, deductions begin with the latter and works back again to particulars, connecting them and binding them together. The inductive movement is toward discovery of a binding principle, the deductive towards its testing, confirming, refuting, modifying it on the basis of its capacity to interpret isolated details into unified experience. So far as we conduct each of these processes in the light of the other, we get valid discovery or verified critical thinking. Illustration from everyday experience. A commonplace illustration may enforce the points of this formula. A man who has left his rooms in order finds them upon his return in a state of confusion, articles being scattered at random. Automatically, the notion comes to his mind that burglary would account for the disorder. He has not seen the burglars; their presence is not a fact of observation, but it is a thought, an idea. Moreover, the man has no special burglars in mind. It is the relation, the meaning of burglary, something general, that comes to mind. The state of his room is perceived and is particular, definite, exactly as it is. Burglars are inferred and have a general status. The state of the room is a fact, certain and speaking for itself. The presence of burglars is a possible meaning which may explain the facts. Of induction. So far, there is an inductive tendency suggested by particular and present facts. In the same inductive way, it occurs to him that his children are mischievous, and that they may have thrown the things about. This rival hypothesis, or conditional principle of explanation, prevents him from dogmatically accepting the first suggestion. Judgment is held in suspense and a positive conclusion postponed. Of deduction. Then deductive movement begins. Further observations, recollections, reasonings are conducted on the basis of a development of the ideas suggested. If burglars were responsible, such and such things would have happened. Articles of value would be missing. Here the man is going from a general principle or relation to special features that accompany it, to particulars, not back, however, merely to the original particulars, which would be fruitless or take him in a circle, but to new details, the actual discovery or non-discovery of which will test the principle. The man turns to a box of valuables. Some things are gone, some, however, are still there. Perhaps he has himself removed the missing articles, but has forgotten it. His experiment is not a decisive test. He thinks of the silver in the sideboard. The children would not have taken that, nor would he absent-mindedly have changed its place. He looks, all the solid ware is gone. The conception of burglars is confirmed. Examination of windows and doors shows that they have been tampered with. Belief culminates. The original isolated facts have been woven into a coherent fabric. The idea first suggested inductively has been employed to reason out hypothetically certain additional particulars not yet experienced that ought to be there if the suggestion is correct. Then new acts of observation have shown that the particulars theoretically called for are present, and by this process the hypothesis is strengthened, corroborated. This moving back and forth between the observed facts and the conditional idea is kept up till a coherent experience of an object is substituted for the experience of conflicting details, or else the whole matter is given up as a bad job. Science is the same operations carefully performed. Sciences exemplify similar attitudes and operations, but with a higher degree of elaboration of the instruments of caution, exactness, and thoroughness. This greater elaboration brings about specialization, an accurate marking off of various types of problems from one another, and a corresponding segregation and classification of the materials of experience associated with each type of problem. We shall devote the remainder of this chapter to a consideration of the devices by which the discovery, the development, and the testing of meanings are scientifically carried on. 2. Guidance of the inductive movement. Guidance is indirect. Control of the formation of suggestion is necessarily indirect, not direct, imperfect, not perfect. Just because all discovery, all apprehension involving thought of the new goes from the known, the present, to the unknown and absent, no rules can be stated that will guarantee correct inference. Just what is suggested to a person in a given situation depends upon his native constitution, his originality, his genius, temperament, the prevalent direction of his interests, his early environment, the general tenor of his past experiences, his special training, the things that have recently occupied him continuously or vividly, and so on, to some extent even upon an accidental conjunction of present circumstances. These matters, so far as they lie in the past or in external conditions, clearly escape regulation. A suggestion simply does or does not occur. This or that suggestion just happens, occurs, springs up. If, however, prior experience and training have developed an attitude of patience in a condition of doubt, a capacity for suspended judgment, and a liking for inquiry, indirect control of the course of suggestions is possible. The individual may return upon, revise, restate, enlarge, and analyze the facts out of which suggestion springs. Inductive methods, in the technical sense, all have to do with regulating the conditions under which observation, memory, and the acceptance of the testimony of others, the operations supplying the raw data, proceed. Method of indirect regulation. Given the facts A, B, C, D on one side and certain individual habits on the other, suggestion occurs automatically. But if the facts A, B, C, D are carefully looked into and thereby resolved into facts A, B, R, S, a suggestion will automatically present itself different from that called up by the facts in their first form. to inventory the facts, to describe exactly and minutely their respective traits, to magnify artificially those that are obscure and feeble, to reduce artificially those that are so conspicuous and glaring as to be distracting. These are ways of modifying the facts that exercise suggestive force, and thereby indirectly guiding the formation of suggested inferences. Illustration from diagnosis. Consider, for example, how a physician makes his diagnosis, his inductive interpretation. If he is scientifically trained, he suspends, postpones, reaching a conclusion in order that he may not be led by superficial occurrences into a snap judgment. Certain conspicuous phenomena may forcibly suggest typhoid, but he avoids a conclusion, or even any strong preference for this or that conclusion, until he has greatly 1. Enlarged the scope of his data, and 2. Rendered them more minute. He not only questions the patient as to his feelings and as to his acts prior to the disease, but by various manipulations with his hands, and with instruments made for the purpose, brings to light a large number of facts of which the patient is quite unaware. The state of temperature, respiration, and heart action is accurately noted, and their fluctuations from time to time are exactly recorded. Until this examination has worked out toward a wider collection, and in toward a minuter scrutiny of details, inference is deferred. Summary. Definition of scientific induction. Scientific induction means, in short, all the processes by which the observing and amassing of data are regulated with a view to facilitating the formation of explanatory conceptions and theories. These devices are all directed toward selecting the precise facts to which weight and significance shall attach in forming suggestions or ideas. Specifically, this selective determination involves devices of 1. Elimination by analysis of what is likely to be misleading and irrelevant, 2. Emphasis of the important by collection and comparison of cases, 3. Deliberate construction of data by experimental variation. Elimination of irrelevant meanings. 1. It is a common saying that one must learn to discriminate between observed facts and judgments based upon them. Taken literally, such advice cannot be carried out. In every observed thing there is, if the thing have any meaning at all, some consolidation of meaning with what is sensibly and physically present, such that, if this were entirely excluded, what is left would have no sense. A says, "I saw my brother." The term brother, however, involves a relation that cannot be sensibly or physically observed. It is inferential in status. If A contents himself with saying, "I saw a man," the factor of classification, of intellectual reference, is less complex, but still exists. If, as a last resort, A were to say, "Anyway, I saw a colored object," some relationship, though more rudimentary and undefined, still subsists. Theoretically, it is possible that no object was there, only an unusual mode of nerve stimulation. Nonetheless, the advice to discriminate what is observed from what is inferred is sound practical advice. Its working import is that one should eliminate or exclude those inferences as to which experience has shown that there is greatest liability to error. This, of course, is a relative matter. Under ordinary circumstances, no reasonable doubt would attach to the observation, "I see my brother." It would be pedantic and silly to resolve this recognition back into more elementary form. Under other circumstances, it might be a perfectly genuine question as to whether A saw even a colored thing, or whether the color was due to a stimulation of the sensory optical apparatus, like seeing stars upon a blow, or to a disordered circulation. In general, the scientific man is one who knows that he is likely to be hurried to a conclusion, and that part of this precipitancy is due to certain habits which tend to make him read certain meanings into situations that confront him, so that he must be on the lookout against errors arising from his interests, habits, and current preconceptions. The technique of conclusion. The technique of scientific inquiry thus consists in various processes that lead to exclude over hasty reading in of meanings, devices that aim to give a purely objective, unbiased rendering of the data to be interpreted. Flushed cheeks usually mean heightened temperature. Paleness means lowered temperature. The clinical thermometer records automatically the actual temperature and hence checks up the habitual associations that might lead to error in a given case. All the instrumentalities of observation, the various meters and graphs and scopes, fill a part of their scientific role in helping to eliminate meanings supplied because of habit, prejudice, the strong momentary preoccupation of excitement and anticipation, and by the vogue of existing theories. Photographs, phonographs, chemographs, actinographs, seismographs, plethysmographs, and the like, moreover, give records that are permanent, so that they can be employed by different persons and by the same person in different states of mind, i.e., under the influence of varying expectations and dominant beliefs. Thus, purely personal propositions due to habit, to desire, to after effects of recent experience, may be largely eliminated. In ordinary language, the facts are objectively, rather than subjectively, determined. In this way, tendencies to premature interpretation are held in check. Collection of instances. 2. Another important method of control consists in the multiplication of cases or instances. If I doubt whether a certain handful gives a fair sample, or representative, for purposes of judging value, of a whole carload of grain, I take a number of handfuls from various parts of the car and compare them. If they agree in quality, well and good. If they disagree, we try to get enough samples so that when they are thoroughly mixed, the result will be a fair basis for an evaluation. This illustration represents roughly the value of that aspect of scientific control in induction which insists upon multiplying observations instead of basing the conclusion upon one or a few cases. This method not the whole of induction. So prominent, indeed, is this aspect of inductive method that it is frequently treated as the whole of induction. It is supposed that all inductive inference is based upon collecting and comparing a number of like cases. But in fact, such comparison and collection is a secondary development within the process of securing a correct conclusion in some single case. If a man infers from a single sample of grain as to the grade of wheat of the car as a whole, it is induction and, under certain circumstances, a sound induction. Other cases are resorted to simply for the sake of rendering that induction more guarded and more probably correct. In like fashion, the reasoning that led up to this burglary idea, in the instance already cited, was inductive, though there was but one single case examined. The particulars upon which the general meaning, or relation, of burglary was grounded were simply the sum total of the unlike items and qualities that made up the one case examined. Had this case presented very great obscurities and difficulties, recourse might then have been had to examination of a number of similar cases. But this comparison would not make inductive a process which was not previously of that character. It would only render induction more wary and adequate. The object of bringing into consideration a multitude of cases is to facilitate the selection of the evidential or significant features upon which to base inference in some single case. Contrast as important as likeness. Accordingly, points of unlikeness are as important as points of likeness among the cases examined. Comparison without contrast does not amount to anything logically. In the degree in which other cases observed or remembered merely duplicate the case in question, we are no better off for purposes of inference than if we had permitted our single original fact to dictate a conclusion. In the case of the various samples of grain, it is the fact that the samples are unlike, at least in the part of the carload from which they are taken, that is important. Were it not for this unlikeness, their likeness in quality would be of no avail in assisting inference. If we are endeavoring to get a child to regulate his conclusions about the germination of a seed by taking into account a number of instances, very little is gained if the conditions in all these instances closely approximate one another. But if one seed is placed in pure sand, another in loam, and another on blotting paper, and if in each case there are two conditions, one with and another without moisture, the unlike factors tend to throw into relief the factors that are significant or essential for reaching a conclusion. Unless, in short, the observer takes care to have the differences in the observed cases as extreme as conditions allow, and unless he notes unlikeness as carefully as likenesses, he has no way of determining the evidential force of the data that confront him. Importance of exceptions and contrary cases. Another way of bringing out this importance of unlikeness is the emphasis put by the scientist upon negative cases, upon instances which it would seem ought to fall into line, but which as a matter of fact do not. Anomalies, exceptions, things which agree in most respects, but disagree in some crucial point, are so important that many of the devices of scientific technique are designed purely to detect, record, and impress upon memory contrasting cases. Darwin remarked that so easy is it to pass over cases that oppose a favorite generalization that he had made it a habit not merely to hunt for contrary instances, but also to write down any exception he noted or thought of, as otherwise it was almost sure to be forgotten. 3. Experimental variation of conditions. Experiment, the typical method of introducing contrast factors. We have already trenched upon this factor of inductive method, the one that is the most important of all wherever it is feasible. Theoretically, one sample case of the right kind will be as good a basis for an inference as 1,000 cases, but cases of the right kind rarely turn up spontaneously. We have to search for them, and we may have to make them. If we take cases just as we find them, whether one case or many cases, they contain much that is irrelevant to the problem in hand, while much that is relevant is obscure, hidden. The object of experimentation is the construction by regular steps taken on the basis of a plan thought out in advance of a typical crucial case, a case formed with express reference to throwing light on the difficulty in question. All inductive methods rest, as already stated, upon regulation of the conditions of observation and memory. Experiment is simply the most adequate regulation possible of these conditions. We try to make the observation such that every factor entering into it, together with the mode and the amount of its operation, may be open to recognition. Such making of observations constitutes experiment. 3 advantages of experiment. Such observations have many and obvious advantages over observation, no matter how extensive, with respect to which we simply wait for an event to happen or an object to present itself. Experiment overcomes the defects due to A, the rarity, B, the subtlety and minuteness or the violence, and C, the rigid fixity of facts as we ordinarily experience them. The following quotations from Jevons's Elementary Lessons in Logic bring out all these points. 1. We might have to wait years or centuries to meet accidentally with facts which we can readily produce at any moment in a laboratory, and it is probable that most of the chemical substances now known, and many excessively useful products, would never have been discovered at all by waiting till nature presented them spontaneously to our observation. This quotation refers to the infrequency or rarity of certain facts of nature, even very important ones. The passage then goes on to speak of the minuteness of many phenomena which make them escape ordinary experience. 2. Electricity doubtless operates in every particle of matter, perhaps at every moment of time, and even the ancients could not but notice its action in the lodestone, in lightning, in the aurora borealis, or in a piece of rubbed amber. But in lightning, electricity was too intense and dangerous. In the other cases, it was too feeble to be properly understood. The science of electricity and magnetism could only advance by getting regular supplies of electricity from the common electric machine or the galvanic battery, and by making powerful electromagnets. Most, if not all, the effects which electricity produces must go on in nature, but altogether too obscurely for observation. Jevons then deals with the fact that, under ordinary conditions of experience, phenomena which can be understood only by seeing them under varying conditions are presented in a fixed and uniform way. 3. Thus, carbonic acid is only met in the form of a gas, proceeding from the combustion of carbon, but when exposed to extreme pressure and cold, it is condensed into a liquid, and may even be converted into a snow-like solid substance. Many other gases have in like manner been liquefied or solidified, and there is reason to believe that every substance is capable of taking all 3 forms of solid, liquid, and gas, if only the conditions of temperature and pressure can be sufficiently varied. Mere observation of nature would have led us, on the contrary, to suppose that nearly all substances were fixed in one condition only, and could not be converted from solid into liquid and from liquid into gas. Many volumes would be required to describe in detail all the methods that investigators have developed in various subjects for analyzing and restating the facts of ordinary experience so that we may escape from capricious and routine suggestions, and may get the facts in such a form and in such a light or context that exact and far-reaching explanations may be suggested in place of vague and limited ones. But these various devices of inductive inquiry all have one goal in mind: the indirect regulation of the function of suggestion, or formation of ideas, and in the main, they will be found to reduce to some combination of the 3 types of selecting and arranging subject matter just described. 4. Guidance of the deductive movement. Value of deduction for guiding induction. Before dealing directly with this topic, we must note the systematic regulation of induction depends upon the possession of a body of general principles that may be applied deductively to the examination or construction of particular cases as they come up. If the physician does not know the general laws of the physiology of the human body, He has little way of telling what is either peculiarly significant or peculiarly exceptional in any particular case that he is called upon to treat. If he knows the laws of circulation, digestion, and respiration, he can deduce the conditions that should normally be found in a given case. These considerations give a baseline from which the deviations and abnormalities of a particular case may be measured. In this way, the nature of the problem at hand is located and defined. Attention is not wasted upon features which, though conspicuous, have nothing to do with the case. It is concentrated upon just those traits which were out of the way and hence require explanation. A question well put is half answered, i.e., a difficulty clearly apprehended is likely to suggest its own solution, while a vague and miscellaneous perception of the problem leads to groping and fumbling. Deductive systems are necessary in order to put the question in a fruitful form. Reasoning a thing out. The control of the origin and development of hypothesis by deduction does not cease, however, with locating the problem. Ideas, as they first present themselves, are inchoate and incomplete. Deduction is their elaboration into fullness and completeness of meaning. The phenomenon which the physician isolates from the total mass of facts that exists in front of him suggests, we will say, typhoid fever. Now this conception of typhoid fever is one that is capable of development. If there is typhoid, wherever there is typhoid, there are certain results, certain characteristic symptoms. By going over mentally the full bearing of the concept of typhoid, the scientist is instructed as to further phenomena to be found. Its development gives him an instrument of inquiry, of observation and experimentation. He can go to work deliberately to see whether the case presents those features that it should have if the supposition is valid. The deduced results form a basis for comparison with observed results. Except where there is a system of principles capable of being elaborated by theoretical reasoning, the process of testing, or proof, of a hypothesis is incomplete and haphazard. Such reasoning implies systematized knowledge. These considerations indicate the method by which the deductive movement is guided. Deduction requires a system of allied ideas which may be translated into one another by regular or graded steps. The question is whether the facts that confront us can be identified as typhoid fever. To all appearances, there is a great gap between them and typhoid. But if we can, by some method of substitutions, go through a series of intermediary terms, the gap may, after all, be easily bridged. Typhoid may mean P, which in turn means O, which means N, which means M, which is very similar to the data selected as the key to the problem. Or definition and classification. One of the chief objects of science is to provide for every typical branch of subject matter a set of meanings and principles so closely interknit that any one implies some other according to definite conditions, under which certain other conditions implies another, and so on. In this way, various substitutions of equivalence are possible, and reasoning can trace out, without having recourse to specific observations, very remote consequences of any suggested principle. Definition, general formulae, and classification are the devices by which the fixation and deliberation of a meaning into its detailed ramifications are carried on. They are not ends in themselves, as they are frequently regarded even in elementary education, but instrumentalities for facilitating the development of a conception into the form where its applicability to given facts may be best tested. The final control of deduction. The final test of deduction lies in experimental observation. Elaboration by reasoning may make a suggested idea very rich and very plausible, but it will not settle the validity of that idea. Only effects can be observed, by methods either of collection or of experimentation, that agree in detail and without exception with the deduced results. Are we justified in accepting the deduction as giving a valid conclusion? Thinking, in short, must end as well as begin in the domain of concrete observations, if it is to be complete thinking, and the ultimate educative value of all deductive processes is measured by the degree to which they become working tools in the creation and development of new experiences. 5. Some educational bearings of the discussion. Educational counterparts of false logical theories. Isolation of facts. Some of the points of the foregoing logical analysis may be clinched by a consideration of their educational implications, especially with reference to certain practices that grow out of a false separation by which each is thought to be independent of the other and complete in itself. 1. In some school subjects, or at all events in some topics or in some lessons, the pupils are immersed in details. Their minds are loaded with disconnected items, whether gleaned by observation and memory or accepted on hearsay and authority. Induction is treated as beginning and ending with the amassing of facts, of particular isolated pieces of information. That these items are educative only as suggesting a view of some larger situation in which the particulars are included and thereby accounted for, is ignored. In object lessons in elementary education and in laboratory instruction in higher education, the subject is often so treated that the student fails to see the forest on account of the trees. Things and their qualities are retailed and detailed without reference to a more general character which they stand for and mean. Or in the laboratory, the student becomes engrossed in the process of manipulation, irrespective of the reason for their performance, without recognizing a typical problem for the solution of which they afford the appropriate method. Only deduction brings out and emphasizes consecutive relationships, and only when relationships are held in view does learning become more than a miscellaneous scrap bag. Failure to follow up by reasoning. 2. Again, the mind is allowed to hurry on to a vague notion of the whole of which the fragmentary facts are portions, without any attempt to become conscious of how they are bound together as parts of this whole. The student feels that, in a general way, as we say, the facts of the history or geography lesson are related thus and so, but in a general way, here stands only for in a vague way, somehow or other, with no clear recognition of just how. The pupil is encouraged to form, on the basis of the particular facts, a general notion, a conception of how they stand related, but no pains are taken to make the student follow up the notion, to elaborate it, and see just what its bearings are upon the case in hand and upon similar cases. The inductive inference, the guess, is formed by the student. If it happens to be correct, it is at once accepted by the teacher, or if it is false, it is rejected. If any amplification of the idea occurs, it is quite likely carried through by the teacher, who thereby assumes the responsibility for its intellectual development. But a complete and integral act of thought requires that the person making the suggestion, the guess, be responsible also for the reasoning out its bearings upon the problem in hand, that he develop the suggestion at least enough to indicate the ways in which it applies to and accounts for the specific data of the case. Too often, when a recitation does not consist in simply testing the ability of the student to display some form of technical skill, or to repeat facts and principles accepted on the authority of textbook or lecturer, the teacher goes on to the opposite extreme, and after calling out the spontaneous reflection of the pupils, their guesses or ideas about the matter, merely accepts or rejects them, assuming himself the responsibility for their elaboration. In this way, the function of suggestion and of interpretation is excited, but it is not directed and trained. Induction is simulated but is not carried over into the reasoning phase necessary to complete it. In other subjects and topics, the deductive phase is isolated and is treated as if it were complete in itself. This false isolation may show itself in either and both of 2 points, namely at the beginning or at the end of the resort to general intellectual procedure. Isolation of deduction by commencing with it. Beginning with definitions, rules, general principles, classifications, and the like, is a common form of the first error. This method has been such a uniform object of attack on the part of all educational reformers that it is not necessary to dwell upon it further than to note that the mistake is, logically, due to the attempt to introduce deductive considerations without first making acquaintance with the particular facts that create a need for the generalizing rational devices. Unfortunately, the reformer sometimes carries his objection too far, or rather locates it in the wrong place. He is led into a tirade against all definition, all systematization, all use of general principles, instead of confining himself to pointing out their futility and their deadness when not properly motivated by familiarity with concrete experiences. Isolation of deduction from direction of new observations. 4. The isolation of deduction is seen, at the other end, wherever there is failure to clinch and test the results of the general reasoning process by application to new concrete cases. The final point of the deductive devices lies in their use in assimilating and comprehending individual cases. No one understands a general principle fully, no matter how adequately he can demonstrate it, to say nothing of repeating it, till he can employ it in the mastery of a new situations, which, if they are new, differ in manifestation from the cases used in reaching the generalization. Too often the textbook or teacher is contented with a series of somewhat perfunctory examples and illustrations, and the student is not forced to carry out the principle that he has formulated over into further cases of his own experience. Insofar, the principle is inert and dead. Lack of provision for experimentation. 5. It is only a variation upon the same theme to say that every complete act of reflective inquiry makes provision for experimentation, for testing suggested and accepted principles by employing them for the active construction of new cases, in which new qualities emerge. Only slowly do our schools accommodate themselves to the general advance of scientific method. From the scientific side, it is only demonstrated that effective and integral thinking is possible only where the experimental method in some form is used. Some recognition of this principle is evinced in higher institutions of learning, colleges, and high schools, but in elementary education it is still assumed, for the most part, that the pupil's natural range of observations, supplemented by what he accepts on hearsay, is adequate for intellectual growth. Of course, it is not necessary that laboratories shall be introduced under the same name, much less that elaborate apparatus be secured, But the entire scientific history of humanity demonstrates that the conditions for complete mental activity will not be obtained till adequate provision is made for the carrying on of activities that actually modify physical conditions, and that books, pictures, and even objects that are passively observed but not manipulated do not furnish the provision required. End of chapter 7. Chapter 8. Judgment. The interpretation of facts. 1. The three factors of judging. Good judgment. A man of good judgment in a given set of affairs is a man in so far educated, trained, whatever may be his literacy. And if our schools turn out their pupils in that attitude of mind which is conducive to good judgment in any department of affairs in which the pupils are placed, they have done more than if they sent out their pupils merely possessed of vast stores of information, or high degrees of skill in specialized branches. To know what is good judgment, we need first to know what judgment is. Judgment and inference. That there is an intimate connection between judgment and inference is obvious enough. The aim of inference is to terminate itself in an adequate judgment of a situation, and the course of inference goes on through a series of partial and tentative judgments. What are these units, these terms of inference, when we examine them on their own account? Their significant traits may be readily gathered from a consideration of the operations to which the word judgment was originally applied, namely, the authoritative decision of matters in legal controversy, the procedure of the judge on the bench. There are three such features. 1. A controversy, consisting of opposite claims regarding the same objective situation. 2. A process of defining and elaborating these claims, and of sifting the facts adduced to support them. 3. A final decision, or sentence, closing the particular matter in dispute, and also serving as a rule or principle for deciding future cases. Uncertainty the antecedent of judgment. 1. Unless there is something doubtful, the situation is read off at a glance. It is taken in on sight, i.e., there is merely apprehension, perception, recognition, not judgment. If the matter is wholly doubtful, if it is dark and obscure throughout, there is a blind mystery, and again no judgment occurs. But if it suggests, however vaguely, different meanings, rival possible interpretations, there is some point at issue, some matter at stake. Doubt takes the form of dispute, controversy. Different sides compete for a conclusion in their favor. Cases brought to trial before a judge illustrate neatly and unambiguously this strife of alternative interpretations. But any case of trying to clear up intellectually a doubtful situation exemplifies the same traits. A moving blur catches our eye in the distance. We ask ourselves, what is it? Is it a cloud of whirling dust? A tree waving its branches? A man signaling to us? Something in the total situation suggests each of these possible meanings. Only one of them can possibly be sound. Perhaps none of them is appropriate, yet some meaning the thing in question surely has. Which of the alternative suggested meanings has the rightful claim? What does the perception really mean? How is it to be interpreted, estimated, appraised, placed? Every judgment proceeds from some such situation. Judgment defines the issue. 2. The hearing of the controversy, the trial, i.e., the weighing of alternative claims, divides into two branches, either of which, in a given case, may be more conspicuous than the other. In the consideration of a legal dispute, these two branches are sifting the evidence and selecting the rules that are applicable. They are the facts and the law of the case. In judgment they are (a) the determination of the data that are important in the given case. Compare the inductive movement. And (b) the elaboration of the conceptions or meanings suggested by the crude data. Compare the deductive movement. (a) What portions or aspects of the situation are significant in controlling the formation of the interpretation? (b) Just what is the full meaning and bearing of the conception that is used as a method of interpretation? These questions are strictly correlative. The answer to each depends upon the answer to the other. We may, however, for convenience, consider them separately. (a) By selecting what facts are evidence. In every actual occurrence, there are many details which are part of the total occurrence, but which, nevertheless, are not significant in relation to the point at issue. All parts of an experience are equally present, but they are very far from being of equal value as signs or as evidences. Nor is there any tag or label on any trait saying, "This is important," or "This is trivial." Nor is intensity, or vividness, or conspicuousness a safe measure of indicative and proving value. The glaring thing may be totally insignificant in this particular situation, and the key to the understanding of the whole matter may be modest or hidden. Features that are not significant are distracting. They proffer their claims to be regarded as clues and cues to interpretation, while traits that are significant do not appear on the surface at all. Hence, judgment is required even in reference to the situation or event that is present to the senses. Elimination or rejection, selection, discovery, or bringing to light must take place. Till we have reached a final conclusion, rejection and selection must be tentative or conditional. We select the things that we hope or trust are cues to meaning. But if they do not suggest a situation that accepts and includes them, we reconstitute our data, the facts of the case. For we mean, intellectually, by the facts of the case, those traits that are used as evidence in reaching a conclusion or forming a decision. Expertness in selecting evidence. No hard and fast rules for this operation of selecting and rejecting, or fixing upon the facts, can be given. It all comes back, as we say, to the good judgment, the good sense, of the one judging. To be a good judge is to have a sense of the relative indicative or signifying values of the various features of the perplexing situation. To know what to let go of, as no account, what to eliminate as irrelevant, what to retain as conducive to outcome, what to emphasize as a clue to the difficulty. This power in ordinary matters we call knack, tact, cleverness. In more important affairs, insight, discernment. In part it is instinctive or inborn, but it also represents the funded outcome of long familiarity with like operations in the past. Possession of this ability to seize what is evidential or significant and to let go the rest is the mark of the expert, the connoisseur, the judge in any matter. Intuitive judgments. Mill cites the following case, which is worth noting as an instance of the extreme delicacy and accuracy to which may be developed this power of sizing up the significant factors of a situation. A Scotch manufacturer procured from England, at a high rate of wages, a working dyer, famous for producing very fine colors, with the view of teaching to his other workmen the same skill. The workmen came, but his method of proportioning the ingredients, in which lay the secrets of the effects he produced, was by taking them up in handfuls, while the common method was to weigh them. The manufacturer sought to make him turn his handling system into an equivalent weighing system, that the general principles of his peculiar mode of proceeding might be ascertained. This, however, the man found himself quite unable to do, and could therefore impart his own skill to nobody. He had, from individual cases of his own experience, established a connection in his mind between the fine effects of color and tactual perceptions in handling his dyeing materials. And from these perceptions he could, in any particular case, infer the means to be employed, and the effects which would be produced. Long brooding over conditions, intimate contact associated with keen interest, thorough absorption in a multiplicity of allied experiences, tend to bring about those judgments which we then call intuitive. But they are true judgments because they are based on intelligent selection and estimation, with the solution of a problem as the controlling standard. Possession of this capacity makes the difference between the artist and the intellectual bungler. Such is judging ability, in its completest form, as to the data of the decision to be reached. But in any case there is a certain feeling along for the way to be followed, a constant tentative picking out of certain qualities to see what emphasis upon them would lead to, a willingness to hold final selection in suspense, and to reject the factors entirely or regulate them to a different position in the evidential scheme if other features yield more solvent suggestions. Alertness, flexibility, curiosity are the essentials. Dogmatism, rigidity, prejudice, caprice, arising from routine, passion, and flippancy, are fatal. b. To decide an issue, the appropriate principles must also be selected. This selection of data is, of course, for the sake of controlling the development and elaboration of the suggested meaning in the light of which they are to be interpreted. An evolution of conceptions thus goes on simultaneously with the determination of the facts. One possible meaning after another is held before the mind, considered in relation to the data to which it is applied, is developed into its more detailed bearings upon the data, is dropped or tentatively accepted and used. We do not approach any problem with a wholly naive or virgin mind. We approach it with certain acquired habitual modes of understanding, with a certain store of previously evolved meanings, or at least of experiences from which meanings may be educed. If the circumstances are such that a habitual response is called directly into play, there is an immediate grasp of meaning. If the habit is checked and inhibited from easy application, a possible meaning for the facts in question presents itself. No hard and fast rules decide whether a meaning suggested is the right and proper meaning to follow up. The individual's own good, or bad, judgment is the guide. There is no label on any given idea or principle which says automatically, "Use me in this situation," as the magic cakes of Alice in Wonderland were inscribed, "Eat me." The thinker has to decide, to choose, and there is always a risk, so that the prudent thinker selects warily. Subject that is, to confirmation or frustration by later events. If one is not able to estimate wisely what is relevant to the interpretation of a given perplexing or doubtful issue, it avails little that arduous learning has built up a large stock of concepts. For learning is not wisdom. Information does not guarantee good judgment. Memory may provide an antiseptic refrigerator in which to store a stock of meanings for future use, but judgment selects and adopts the one used in a given emergency, and without any emergency, some crisis, slight or great, there is no call for judgment. No conception, even if it is carefully and firmly established in the abstract, can at first safely be more than a candidate for the office of interpreter. Only greater success than that of its rivals in clarifying dark spots, untying hard knots, reconciling discrepancies, can elect it or prove it a valid idea for the given situation. Judging terminates in a decision or statement. 3. The judgment when formed is a decision. It closes or concludes the question at issue. This determination not only settles the particular case, but it helps fix a rule or method for deciding similar matters in the future, as the sentence of the judge on the bench both terminates that dispute and also forms a precedent for future decisions. If the interpretation settled upon is not controverted by subsequent events, a presumption is built up in favor of similar interpretation in other cases, where the features are not so obviously unlike as to make it inappropriate. In this way, principles of judging are gradually built up. A certain manner of interpretation gets weight, authority. In short, meanings get standardized. They become logical concepts. 2. The origin and nature of ideas. Ideas are conjectures employed in judging. This brings us to the question of ideas in relation to judgments. Something in an obscure situation suggests something else as its meaning. If this meaning is at once accepted, there is no reflective thinking, no genuine judging. Thought is cut short uncritically. Dogmatic belief, with all its attending risks, takes place. But if the meaning suggested is held in suspense, pending examination and inquiry, there is true judgment. We stop and think. We defer conclusion in order to infer more thoroughly. In this process of being only conditionally accepted, accepted only for examination, meanings become ideas. That is to say, an idea is a meaning that is tentatively entertained, formed, and used with reference to its fitness to decide a perplexing situation, a meaning used as a tool of judgment, or tools of interpretation. Let us recur to our instance of a blur in motion appearing at a distance. We wonder what the thing is, i.e., what the blur means. A man waving his arms, a friend beckoning to us, are suggested as possibilities. To accept at once either alternative is to arrest judgment. But if we treat what is suggested as only a suggestion, a supposition, a possibility, it becomes an idea having the following traits. A. As merely a suggestion, it is a conjecture, a guess, which in cases of greater dignity we call a hypothesis or a theory. That is to say, it is a possible but as yet doubtful mode of interpretation. B. Even though doubtful, it has an office to perform, namely that of directing inquiry and examination. If this blur means a friend beckoning, then careful observation should show certain other traits. If it is a man driving unruly cattle, certain other traits should be found. Let us look and see if these traits are found. Taken merely as a doubt, an idea would paralyze inquiry. Taken merely as a certainty, it would arrest inquiry. Taken as a doubtful possibility, it affords a standpoint, a platform, a method of inquiry. Pseudo-ideas. Ideas are not, then, genuine ideas unless they are tools in a reflective examination which tends to solve a problem. Suppose it is a question of having the pupil grasp the idea of the sphericity of the earth. This is different from teaching him its sphericity as a fact. He may be shown, or reminded of, a ball or a globe, and be told that the earth is round like those things. He may then be made to repeat that statement day after day, till the shape of the earth and the shape of the ball are welded together in his mind. But he has not thereby acquired any idea of the earth's sphericity. At most, he has had a certain image of a sphere, and has finally managed to image the earth after the analogy of his ball image. To grasp sphericity as an idea, the pupil must first have realized certain perplexities or confusing features in observed facts, and have had the idea of spherical shape suggested to him as a possible way of accounting for the phenomena in question. Only by use as a method of interpreting data so as to give them fuller meaning does sphericity become a genuine idea. There may be a vivid image and no idea, or there may be a fleeting, obscure image and yet an idea, if that image performs the function of instigating and directing the observation and relation of facts. Ideas furnish the only alternative to hit or miss methods. Logical ideas are like keys which are shaping with reference to opening a lock. Pike, separated by a glass partition from the fish upon which they ordinarily prey, will, so it is said, butt their heads against the glass until it is literally beaten into them that they cannot get at their food. Animals learn, when they learn at all, by a cut and try method, by doing at random first one thing and then another thing, and then preserving the things that happen to succeed. Action directed consciously by ideas, by suggested meanings accepted for the sake of experimenting with them, is the sole alternative both to bull-headed stupidity and to learning bought from that dear teacher, chance experience. They are methods of indirect attack. It is significant that many words for intelligence suggest the idea of circuitous, evasive activity, often with a sort of intimation of even moral obliquity. The bluff, hardy man goes straight, and stupidly, it is implied, at some work. The intelligent man is cunning, shrewd, crooked, wily, subtle, crafty, artful, designing. The idea of indirection is involved. An idea is a method of evading, circumventing, or surmounting, through reflection, obstacles that otherwise would have to be attacked by brute force. But ideas may lose their intellectual quality as they are habitually used. When a child was first learning to recognize, in some hesitating suspense, cats, dogs, houses, marbles, trees, shoes, and other objects, ideas, conscious and tentative meanings, intervened as methods of identification. Now, as a rule, the thing and the meaning are so completely fused that there is no judgment and no idea proper, but only automatic recognition. On the other hand, things that are, as a rule, directly apprehended and familiar become subjects of judgment when they present themselves in unusual contexts. as forms, distances, sizes, positions when we attempt to draw them, triangles, squares, and circles when they turn up not in connection with familiar toys, implements, and utensils, but as problems in geometry. 3. Analysis and synthesis. Judging clears up things. Analysis. Through judging, confused data are cleared up, and seemingly incoherent and disconnected facts brought together. Things may have a peculiar feeling for us. They may make a certain indescribable impression upon us. The thing may feel round, that is, present a quality which we afterwards define as round. An act may seem rude, or what we afterwards classify as rude, and yet this quality may be lost, absorbed, blended, in the total value of the situation. Only as we need to use just that aspect of the original situation as a tool of grasping something perplexing or obscure in another situation, do we abstract or detach the quality so that it becomes individualized. Only because we need to characterize the shape of some new object or the moral quality of some new act, does the element of roundness or rudeness in the old experience detach itself and stand out as a distinctive feature. If the element thus selected clears up what is otherwise obscure in the new experience, if it settles what is uncertain, it thereby itself gains in positiveness and definiteness of meaning. This point will meet us again in the following chapter. Here we shall speak of the matter only as it bears upon the questions of analysis and synthesis. Mental analysis is not like physical division. Misapprehension of analysis in education. Even when it is definitely stated that intellectual and physical analyses are different sorts of operations, intellectual analysis is often treated after the analogy of physical, as if it were the breaking up of a whole into all its constituent parts in the mind instead of in space. As nobody can possibly tell what breaking a whole into its parts in the mind means, this conception leads to the further notion that logical analysis is a mere enumeration and listing of all conceivable qualities and relations. The influence upon education of this conception has been very great. Every subject in the curriculum has passed through, or still remains in, what may be called the phase of anatomical or morphological method, the stage in which understanding this subject is thought to consist of multiplying distinctions of quality, form, relation, and so on, and attaching some name to each distinguished element. In normal growth, specific properties are emphasized and so individualized only when they serve to clear up a present difficulty. Only as they are involved in judging some specific situation is there any motive or use for analyses, i.e., for emphasis upon some element or relation as peculiarly significant. Effects of premature formulation. The same putting the cart before the horse, the product before the process, is found in that overconscious formulation of methods of procedure so current in elementary instruction. The method that is employed in discovery, in reflective inquiry, cannot possibly be identified with the method that emerges after the discovery is made. In the genuine operation of inference, the mind is in the attitude of search, of hunting, of projection, of trying this and that. When the conclusion is reached, the search is at an end. The Greeks used to discuss, how is learning or inquiry possible? For either we know already what we are after, and then we do not learn or inquire, or we do not know, and then we cannot inquire, for we do not know what to look for. The dilemma is at least suggestive, for it points to the true alternative, the use in inquiry of doubt, of tentative suggestion, of experimentation. After we have reached the conclusion, a reconsideration of the steps of the process to see what is helpful, what is harmful, what is merely useless, will assist in dealing more promptly and efficaciously with analogous problems in the future. In this way, more or less explicit method is gradually built up. Compare the earlier discussion of the psychological and the logical. Method comes before its formulation. It is, however, a common assumption that unless the pupil from the outset consciously recognizes and explicitly states the method logically implied in the result he is to reach, he will have no method, and his mind will work confusedly or anarchically, while if he accompanies his performance with conscious statement of some form of procedure, outline, topical analysis, list of headings and subheadings, uniform formula, his mind is safeguarded and strengthened. As a matter of fact, the development of an unconscious logical attitude and habit must come first. A conscious setting forth of the method logically adapted for reaching an end is possible only after the result has first been reached by more unconscious and tentative methods, while it is valuable only when a review of the method that achieved success in a given case will throw light upon a new, similar case. The ability to fasten upon and single out, abstract, analyze, those features of one experience which are logically best is hindered by a premature insistence upon their explicit formulation. It is repeated use that gives a method definiteness, and given this definiteness, precipitation into formulated statement should follow naturally. But because teachers find that the things which they themselves best understand are marked off and defined in clear-cut ways, our schoolrooms are pervaded with the superstition that children are to begin with already crystallized formulae of method. Judgment reveals the bearing or significance of facts. Synthesis. As analysis is conceived to be a sort of picking to pieces, so synthesis is thought to be a sort of physical piecing together, and so imagined, it also becomes a mystery. In fact, synthesis takes place wherever we grasp the bearing of facts on a conclusion, or of a principle on facts. As analysis is emphasis, so synthesis is placing. The one causes the emphasized fact or property to stand out as significant. The other gives what is selected its context, or its connection with what is signified. Every judgment is analytic in so far as it involves discernment, discrimination, marking off of the trivial from the important, the irrelevant form from what points to a conclusion, and it is synthetic in so far as it leaves the mind with an inclusive situation within which the selected facts are placed. Analysis and synthesis are correlative. Educational methods that pride themselves on being exclusively analytic or exclusively synthetic are therefore, so far as they carry out their boasts, incompatible with normal operations of judgment. Discussions have taken place, for example, as to whether the teaching of geography should be analytic or synthetic. The synthetic method is supposed to begin with the partial, limited portion of the earth's surface already familiar to the pupil, and then gradually piece on adjacent regions, the county, the country, the continent, and so on, till an idea of the entire globe is reached, or of the solar system that includes the globe. The analytic method is supposed to begin with the physical whole, the solar system or globe, and to work down through its constituent portions till the immediate environment is reached. The underlying conceptions are of physical wholes and physical parts. As a matter of fact, we cannot assume that the portion of the earth already familiar to the child is such a definite object, mentally, that he can at once begin with it. His knowledge of it is misty and vague as well as incomplete. Accordingly, mental progress will involve analysis of it, emphasis of the features that are significant, so that they will stand out clearly. Moreover, his own locality is not sharply marked off, neatly bounded, and measured. His experience of it is already an experience that involves sun, moon, and stars as parts of the scene he surveys. It involves the changing horizon line as he moves about. That is, even his more limited and local experience involves far-reaching factors that take his imagination clear beyond his own street and village. Connection, relationship with a larger whole, is already involved. But his recognition of these relations is inadequate, vague, incorrect. He needs to utilize the features of the local environment which are understood to help clarify and enlarge his conceptions of the larger geographical scene to which they belong. At the same time, not till he has grasped the larger scene will many of even the commonest features of his environment become intelligible. Analysis leads to synthesis, while synthesis perfects analysis. As the pupil grows in comprehension of the vast, complicated earth in its setting in space, he also sees more definitely the meaning of the familiar local details. This intimate interaction between the selective emphasis and interpretation of what is selected is found wherever reflection proceeds normally. Hence the folly of trying to set analysis and synthesis over against each other. End of chapter 8. Chapter 9. Meaning or Conceptions and Understanding. The place of meanings in mental life. Meaning is central. As in our discussion of judgment we were making more explicit what is involved in inference, so in the discussion of meaning we are only recurring to the central function of all reflection. For one thing to mean, signify, betoken, indicate, or point to, another we saw at the outset to be the essential mark of thinking. To find out what facts, just as they stand, mean, is the object of all discovery. To find out what facts will carry out, substantiate, support a given meaning, is the object of all testing. When inference reaches a satisfactory conclusion, we attain a goal of meaning. The act of judging involves both the growth and the application of meanings. In short, in this chapter we are not introducing a new topic. We are only coming to closer quarters with what hitherto has been constantly assumed. In the first section, we shall consider the equivalence of meaning and understanding, and the two types of understanding, direct and indirect. 1. Meaning and understanding. To understand is to grasp meaning. If a person comes suddenly into your room and calls out paper, various alternatives are possible. If you do not understand the English language, there is simply a noise which may or may not act as a physical stimulus and irritant. But the noise is not an intellectual object. It does not have intellectual value. To say that you do not understand it and that it has no meaning are equivalents. If the cry is the usual accompaniment of the delivery of the morning paper, the sound will have meaning, intellectual content. You will understand it. Or if you are eagerly awaiting the receipt of some important document, you may assume that the cry means an announcement of its arrival. If, in the third place, you understand the English language, but no context suggests itself from your habits and expectations, the word has meaning, but not the whole event. You are then perplexed and incited to think out, to hunt for, some explanation of the apparently meaningless occurrence. If you find something that accounts for the performance, it gets meaning. You come to understand it. As intelligent beings, we presume the existence of meaning, and its absence is an anomaly. Hence, if it should turn out that the person merely meant to inform you that there was a scrap of paper on the sidewalk, or that paper existed somewhere in the universe, you would think him crazy or yourself the victim of a poor joke. To grasp a meaning, to understand, to identify a thing in a situation in which it is important, are thus equivalent terms. They express the nerves of our intellectual life. Without them there is A. Lack of intellectual content, or B. Intellectual confusion and perplexity, or else C. Intellectual perversion, nonsense, insanity. Knowledge and meaning. All knowledge, all science, thus aims to grasp the meaning of objects and events, and this process always consists in taking them out of their apparent brute isolation as events, and finding them to be parts of some larger whole suggested by them, which in turn accounts for, explains, interprets them, i.e., renders them significant. Suppose that a stone with peculiar markings has been found. What do these scratches mean? So far as the object forces the raising of this question, it is not understood, while so far as the color and form that we see mean to us a stone, the object is understood. It is such peculiar combinations of the understood and the non-understood that provoke thought. If at the end of the inquiry the markings are decided to mean glacial scratches, obscure and perplexing traits have been translated into meanings already understood, namely, the moving and grinding power of large bodies of ice and the friction thus induced of one rock upon another. Something already understood in one situation has been transferred and applied to what is strange and perplexing in another, and thereby the latter has become plain and familiar, i.e., understood. This summary illustration discloses that our power to think effectively depends upon possession of a capital fund of meanings which may be applied when desired. Compare what was said about deduction. 2. Direct and indirect understanding. Direct and circuitous understanding. In the above illustrations, two types of grasping of meaning are exemplified. When the English language is understood, the person grasps at once the meaning of paper. He may not, however, see any meaning or sense in the performance as a whole. Similarly, the person identifies the object on sight as a stone. There is no secret, no mystery, no perplexity about that, but he does not understand the markings on it. They have some meaning, but what is it? In one case, owing to familiar acquaintance, the thing and its meaning, up to a certain point, are one. In the other, the thing and its meaning are, temporarily at least, sundered, and meaning has to be sought in order to understand the thing. In one case understanding is direct, prompt, immediate. In the other, it is roundabout and delayed. Interaction of the two types. Most languages have two sets of words to express these two modes of understanding, one for the direct taking in or grasping of meaning, the other for its circuitous apprehension. Thus, inone and ithene in Greek, noscere and scire in Latin, kennen and wissen in German, connaître and savoir in French, while in English to be acquainted with and to know of or about have been suggested as equivalents. Now, our intellectual life consists of a peculiar interaction between these two types of understanding. All judgment, all reflective inference, presupposes some lack of understanding, a partial absence of meaning. We reflect in order that we may get hold of the full and adequate significance of what happens. Nevertheless, something must be already understood, the mind must be in possession of some meaning which it has mastered, or else thinking is impossible. We think in order to grasp meaning, but none the less every extension of knowledge makes us aware of blind and opaque spots, where with less knowledge all had seemed obvious and natural. A scientist brought into a new district will find many things that he does not understand, where the native savage or rustic will be wholly oblivious to any meanings beyond those directly apparent. Some Indians brought to a large city remained stolid at the sight of mechanical wonders of bridge, trolley, and telephone, but were held spellbound by the sight of workmen climbing poles to repair wires. Increase of the store of meanings makes us conscious of new problems, while only through translation of the new perplexities into what is already familiar and plain do we understand or solve these problems. This is the constant spiral movement of knowledge. Intellectual progress a rhythm. Our progress in genuine knowledge always consists in part in the discovery of something not understood in what had previously been taken for granted as plain, obvious, matter of course, and in part in the use of meanings that are directly grasped without question, as instruments for getting hold of obscure, doubtful, and perplexing meanings. No object is so familiar, so obvious, so commonplace that it may not unexpectedly present, in a novel situation, some problem, and thus arouse reflection in order to understand it. No object or principle is so strange, peculiar, or remote that it may not be dwelt upon till its meaning becomes familiar, taken in on sight without reflection. We may come to see, perceive, recognize, grasp, seize, lay hold of principles, laws, abstract truths, i.e., to understand their meaning in very immediate fashion. Our intellectual progress consists, as has been said, in a rhythm of direct understanding, technically called apprehension, with indirect, mediated understanding, technically called comprehension. 2. The process of acquiring meanings. Familiarity. The first problem that comes up in connection with direct understanding is how a store of directly apprehensible meanings is built up. How do we learn to view things on sight as significant members of a situation, or as having, as a matter of course, specific meanings? Our chief difficulty in answering this question lies in the thoroughness with which the lesson of familiar things has been learnt. Thought can more easily traverse an unexplored region than it can undo what has been so thoroughly done as to be ingrained in unconscious habit. We apprehend chairs, tables, books, trees, horses, clouds, stars, rain, so promptly and directly that it is hard to realize that as meanings they had once to be acquired. The meanings are now so much parts of the things themselves. Confusion is prior to familiarity. In an often quoted passage, Mr. James has said, "The baby, assailed by eyes, ears, nose, skin, and entrails at once, feels it all as one great blooming, buzzing confusion." Mr. James is speaking of a baby's world taken as a whole. The description, however, is equally applicable to the way of any new thing strikes an adult, so far as the thing is really new and strange. To the traditional cat in a strange garret, everything is blurred and confused. The wonted marks that label things so as to separate them from one another are lacking. Foreign languages that we do not understand always seem jabberings, babblings, in which it is impossible to fix a definite, clear-cut, individualized group of sounds. The countryman in the crowded city street, the landlubber at sea, the ignoramus in sport at a contest between experts in a complicated game, are further instances. Put an unexperienced man in a factory, and at first the work seems to him a meaningless medley. All strangers of another race proverbially look alike to the visiting foreigner. Only gross differences of size or color are perceived by an outsider in a flock of sheep, each of which is perfectly individualized to the shepherd. A diffusive blur and an indiscriminately shifting suction characterize what we do not understand. The problem of the acquisition of meaning by things, or stated in another way, of forming habits of simple apprehension, is thus the problem of introducing (1) definiteness and distinction, and (2) consistency or stability of meaning into what is otherwise vague and wavering. Practical responses clarify confusion. The acquisition of definiteness and of coherency or constancy of meanings is derived primarily from practical activities. By rolling an object, the child makes its roundness appreciable. By bouncing it, he singles out its elasticity. By throwing it, he makes weight its conspicuous, distinctive factor. Not through the senses, but by means of the reaction, the responsive adjustment, is the impression made distinctive, and given a character marked off from other qualities that call out unlike reactions. Children, for example, are usually quite slow in apprehending differences of color. Differences from the standpoint of the adult so glaring that it is impossible not to note them are recognized and recalled with great difficulty. Doubtless they do not all feel alike, but there is no intellectual recognition of what makes the difference. The redness or greenness or blueness of the object does not tend to call out a reaction that is sufficiently peculiar to give prominence or distinction to the color trait. Gradually, however, certain characteristic habitual responses associate themselves with certain things. The white becomes the sign, say, of milk and sugar, to which the child reacts favorably. Blue becomes the sign of a dress that the child likes to wear, and so on. And the distinctive reactions tend to single out color qualities from other things in which they had been submerged. We identify by use or function. Take another example. We have little difficulty in distinguishing from one another rakes, hoes, plows and harrows, shovels and spades. Each has its own associated characteristic use and function. We may have, however, great difficulty in recalling the difference between serrate and dentate, ovoid and obovoid, in the shapes and edges of leaves, or between acids in ick and in us. There is some difference, but just what? Or, we know what the difference is, but which is which? Variations in form, size, color, and arrangements of parts have much less to do, and the uses, purposes, and functions of things and of their parts much more to do, with distinctness of character and meaning than we should be likely to think. What misleads us is the fact that the qualities of form, size, color, and so on are now so distinct that we fail to see that the problem is precisely to account for the way in which they originally obtained their definiteness and conspicuousness. So far as we sit passive before objects, they are not distinguished out of a vague blur which swallows them all. Differences in the pitch and intensity of sounds leaves behind a different feeling, but until we assume different attitudes toward them, or do something special in reference to them, their vague differences cannot be intellectually gripped and retained. Children's drawings illustrate domination by value. Children's drawings afford a further exemplification of the same principle. Perspective does not exist, for the child's interest is not in pictorial representation, but in the things represented, and while perspective is essential to the former, it is no part of the characteristic uses and values of the things themselves. The house is drawn with transparent walls because the rooms, chairs, beds, people inside are the important things in the house meaning. Smoke always comes out of the chimney, otherwise, why have a chimney at all? At Christmas time, the stockings may be drawn almost as large as the house, or even so large that they have to be put outside of it. In any case, it is the scale of values in use that furnishes the scale for their qualities, the pictures being diagrammatic reminders of these values, not impartial records of physical and sensory qualities. One of the chief difficulties felt by most persons in learning the art of pictorial representation is that habitual uses and results of use have become so intimately read into the character of things that it is practically impossible to shut them out at will. As do sounds used as language signs. The acquiring of meaning by sounds, in virtue of which they become words, is perhaps the most striking illustration that can be found of the way in which mere sensory stimuli acquire definiteness and constancy of meaning and are thereby themselves defined and interconnected for purposes of recognition. Language is a specially good example because there are hundreds or even thousands of words in which meaning is now so thoroughly consolidated with physical qualities as to be directly apprehended, while in the case of words it is easier to recognize that this connection has been gradually and laboriously acquired than in the case of physical objects such as chairs, tables, buttons, trees, stones, hills, flowers, and so on, where it seems as if the union of intellectual character and meaning with the physical fact were aboriginal, and thrust upon us passively rather than acquired through active explorations. And in the case of the meaning of words, we see readily that it is by making sounds and noting the results which follow, by listening to the sounds of others and watching the activities which accompany them, that a given sound finally becomes the stable bearer of a meaning. Summary. Familiar acquaintance with meanings thus signifies that we have acquired in the presence of objects definite attitudes of response which lead us, without reflection, to anticipate certain possible consequences. The definiteness of the expectation defines the meaning, or takes it out of the vague and pulpy; its habitual, recurrent character gives the meaning constancy, stability, consistency, or takes it out of the fluctuating and wavering. 3. Conceptions and meaning. A conception is a definite meaning. The word meaning is a familiar everyday term. The words conception, notion are both popular and technical terms. Strictly speaking, they involve, however, nothing new. Any meaning sufficiently individualized to be directly grasped and readily used, and thus fixed by a word, is a conception or notion. Linguistically, every common noun is the carrier of a meaning, while proper nouns and common nouns with the word this or that prefixed refer to the things in which the meanings are exemplified. That thinking both employs and expands notions, conceptions, is then simply saying that in inference and judgment we use meanings, and that this use also corrects and widens them. Which is standardized. Various persons talk about an object not physically present, and yet all get the same material of belief. The same person in different moments often refers to the same object or kind of objects. The sense experience, the physical conditions, the psychological conditions vary, but the same meaning is conserved. If pounds arbitrarily changed their weight, and foot rules their length, while we were using them, obviously we could not weigh or measure. This would be our intellectual position if meanings could not be maintained with a certain stability and constancy through a variety of physical and personal changes. By it we identify the unknown and supplement the sensibly present, and also systematize things. To insist upon the fundamental importance of conceptions would, accordingly, only repeat what has been said. We shall merely summarize, saying that conceptions, or standard meanings, are instruments 1. Of identification, 2. Of supplementation, and 3. Of placing in a system. Suppose a little speck of light, hitherto unseen, is detected in the heavens. Unless there is a store of meanings to fall back upon as tools of inquiry and reasoning, that speck of light will remain just what it is to the senses, a mere speck of light. For all that it leads to, it might as well be a mere irritation of the optic nerve. Given the stock of meanings acquired in prior experience, this speck of light is mentally attacked by means of appropriate concepts. Does it indicate asteroid or comet, or a new forming sun, or a nebula resulting from some cosmic collision or disintegration? Each of these conceptions has its own specific and differentiating characters, which are then sought for by minute and persistent inquiry. As a result, then, the speck is identified, we will say, as a comet. Through a standard meaning, it gets identity and stability of character. Supplementation then takes place. All the known qualities of comets are read into this particular thing, even though they have not been as yet observed. All that the astronomers of the past have learned about the paths and structure of comets becomes available capital with which to interpret the speck of light. Finally, this comet meaning is itself not isolated, it is a related portion of the whole system of astronomic knowledge. Suns, planets, satellites, nebulae, comets, meteors, stardust, all these conceptions have a certain mutuality of reference and interaction, and when the speck of light is identified as meaning a comet, it is at once adopted as a full member in this vast kingdom of beliefs. Importance of system to knowledge. Darwin, in an autobiographical sketch, says that when a youth he told the geologist Sidgwick of finding a tropical shell in a certain gravel pit. Thereupon Sidgwick said it must have been thrown there by some person, adding, "But if it were really embedded there, it would be the greatest misfortune to geology, because it would overthrow all what we know about the superficial deposits of the Midland counties, since they were glacial." And then Darwin adds, "I was then utterly astonished at Sidgwick not being delighted at so wonderful a fact as a tropical shell being found near the surface in the middle of England. Nothing before had made me thoroughly realize that science consists in grouping facts so that general laws or conclusions may be drawn from them." This instance, which might, of course, be duplicated from any branch of science, indicates how scientific notions make explicit the systematizing tendency involved in use of all concepts. 4. What conceptions are not. The idea that a conception is a meaning that supplies a standard rule for the identification and placing of particulars may be contrasted with some current misapprehensions of its nature. A concept is not a bare residue. 1. Conceptions are not derived from a multitude of different definite objects by leaving out the qualities in which they differ and retaining those in which they agree. The origin of concepts is sometimes described to be as if a child began with a lot of different particular things, say particular dogs, his own Fido, his neighbor's Carlo, his cousin's Tray. Having all these different objects before him, he analyzes them into a lot of different qualities, say A color, B size, C shape, D number of legs, E quantity and quality of hair, F digestive organs, and so on, and then strikes out all the unlike qualities, such as color, size, shape, hair, retaining traits such as quadruped and domesticated, which they all have in general. But an active attitude. As a matter of fact, the child begins with whatever significance he has got out of the one dog he has seen, heard, and handled. He has found that he can carry over from one experience of this object to subsequent experience certain expectations of certain characteristic modes of behavior, may expect these even before they show themselves. He tends to assume this attitude of anticipation whenever any clue or stimulus presents itself, whenever the object gives him any excuse for it. Thus he might call cats little dogs, or horses big dogs, but finding that other expected traits and modes of behavior are not fulfilled, he is forced to throw out certain traits from the dog meaning, while by contrast certain other traits are selected and emphasized. As he further applies the meaning to other dogs, the dog meaning gets still further defined and refined. He does not begin with a lot of ready-made objects from which he extracts a common meaning. He tries to apply to every new experience whatever from his old experience will help him understand it. And as this process of constant assumption and experimentation is fulfilled and refuted by results, his conceptions get body and clearness. It is general because of its application. 2. Similarly, conceptions are general because of their use and application, not because of their ingredients. The view of the origin of conception in an impossible sort of analysis has as its counterpart the idea that the conception is made up out of all the like elements that remain after dissection of a number of individuals. Not so. The moment a meaning is gained, it is a working tool of further apprehensions, an instrument of understanding other things. Thereby the meaning is extended to cover them. Generality resides in application to the comprehension of new cases, not in constituent parts. A collection of traits left as the common residuum, the caput mortuum, of a million objects would be merely a collection an inventory, or aggregate, not a general idea. A striking trait emphasized in any one experience which then served to help understand some other experience would become, in virtue of that service of application, in so far general. Synthesis is not a matter of mechanical addition, but of application of something discovered in one case to bring other cases into line. 5. Definition and organization of meanings. Definiteness versus vagueness. In the abstract meaning is intension. In its application, it is extension. A being that cannot understand at all is at least protected from misunderstandings. But beings that get knowledge by means of inferring and interpreting, by judging what things signify in relation to one another, are constantly exposed to the danger of misapprehension, misunderstanding, mistaking, taking a thing amiss. A constant source of misunderstanding and mistake is indefiniteness of meaning. Through vagueness of meaning, we misunderstand other people, things, and ourselves. Through its ambiguity, we distort and pervert. Conscious distortion of meaning may be enjoyed as nonsense. Erroneous meanings, if clear cut, may be followed up and got rid of. But vague meanings are too gelatinous to offer matter for analysis, and too pulpy to afford support to other beliefs. They evade testing and responsibility. Vagueness disguises the unconscious mixing together of different meanings, and facilitates the substitution of one meaning for another, and covers up the failure to have any precise meaning at all. It is the aboriginal logical sin, the source from which flow most bad intellectual consequences. Totally to eliminate indefiniteness is impossible. To reduce it in extent and in force requires sincerity and vigor. To be clear or perspicuous, a meaning must be detached, single, self-contained, homogeneous, as it were, throughout. The technical name for any meaning which is thus individualized is intension. The process of arriving at such units of meaning, and of stating them when reached, is definition. The intention of the terms man, river, seed, honesty, capital, Supreme Court, is the meaning that exclusively and characteristically attaches to those terms. This meaning is set forth in the definitions of those words. The test of the distinctness of a meaning is that it shall successfully mark off a group of things that exemplify the meaning from other groups, especially of those objects that convey nearly allied meanings. The river meaning, or character, must serve to designate the Rhone, the Rhine, the Mississippi, the Hudson, the Wabash, in spite of their varieties of place, length, quality of water, and must be such as not to suggest ocean currents, ponds, or brooks. This use of a meaning to mark off and group together a variety of distinct existences constitutes its extension. Definition and division. As definition sets forth intension, so division, or the reverse process, classification, expounds extension. Intension and extension, definition and division, are clearly correlative. In language previously used, intension is meaning as a principle of identifying particulars. Extension is the group of particulars identified and distinguished. Meaning as extension would be wholly in the air or unreal did it not point to some object or group of objects, while objects would be as isolated and independent intellectually as they seem to be spatially, Were they not bound into groups or classes on the basis of characteristic meanings which they constantly suggest and exemplify? Taken together, definition and division put us in possession of individualized or definite meanings and indicate to what group of objects meanings refer. They typify the fixation and the organization of meanings. In the degree in which the meanings of any set of experiences are so cleared up as to serve as principles for grouping those experiences in relation to one another, that set of particulars becomes a science, i.e., definition and classification are the marks of a science, as distinct from both unrelated heaps of miscellaneous information and from the habits that introduce coherence into our experience without our being aware of their operation. Definitions are of three types: denotative, expository, scientific. Of these, the first and third are logically important, while the expository type is socially and pedagogically important as an intervening step. We define by picking out: 1. Denotative. A blind man can never have an adequate understanding of the meaning of color and red. A seeing person can acquire the knowledge only by having certain things designated in such a way as to fix attention upon some of their qualities. This method of delimiting a meaning by calling out a certain attitude toward objects may be called denotative or indicative. It is required for all sense qualities, sounds, tastes, colors, and equally for all emotional and moral qualities. The meanings of honesty, sympathy, hatred, fear, must be grasped by having them presented in an individual's first-hand experience. The reaction of educational reformers against linguistic and bookish training has always taken the form of demanding recourse to personal experience. However advanced the person is in knowledge and in scientific training, understanding of a new subject, or a new aspect of an old subject, must always be through these acts of experiencing directly the existence or quality in question, and also by combining what is already more definite. 2. Expository. Given a certain store of meanings which have been directly or denotatively marked out, language becomes a resource by which imaginative combinations and variations may be built up. A color may be defined to one who has not experienced it as lying between green and blue. A tiger may be defined, i.e., the idea of it made more definite, by selecting some qualities from known members of the cat tribe and combining them with qualities of size and weight derived from other objects. Illustrations are of the nature of expository definitions. So are the accounts of meanings given in a dictionary. By taking better known meanings and associating them, the attained store of meanings of the community in which one resides is put at one's disposal. But in themselves these definitions are second-hand and conventional. There is danger that instead of inciting one to effort after personal experiences that will exemplify and verify them, they will be accepted on authority as substitutes. And by discovering method of production. 3. Scientific. Even popular definitions serve as rules for identifying and classifying individuals, but the purpose of such identifications and classifications is mainly practical and social, not intellectual. To conceive the whale as fish does not interfere with the success of whalers, nor does it prevent recognition of a whale when seen, while to conceive it not as fish, but as mammal, serves the practical end equally well, and also furnishes a much more valuable principle for scientific identification and classification. Popular definitions select certain fairly obvious traits as keys to classification. Scientific definitions select conditions of causation, production, and generation as their characteristic material. The traits used by the popular definition do not help us understand why an object has its common meanings and qualities. They simply state the fact that it does have them. Causal and genetic definitions fix upon the way an object is constructed as the key to its being a certain kind of object, and thereby explain why it has its class or common traits. Contrast of causal and descriptive definitions. Science is the most perfect type of knowledge because it uses causal definitions. If, for example, a layman of considerable practical experience were asked what he meant or understood by metal, he would probably reply in terms of the qualities useful: 1. In recognizing any given metal, and 2. In the arts. Smoothness, hardness, glossiness, and brilliancy, heavy weight for its size, would probably be included in his definition, because such traits enable us to identify specific things when we see and touch them. The serviceable properties of capacity for being hammered and pulled without breaking, of being softened by heat and hardened by cold, of retaining the shape and form given, of resistance to pressure and decay, would probably be included, whether or not such terms as malleable or fusible were used. Now a scientific conception, instead of using, even with additions, traits of this kind, determines meaning on a different basis. The present definition of metal is about like this. Metal means any chemical element that enters into a combination with oxygen so as to form a base, i.e., a compound that combines with an acid to form a salt. This scientific definition is founded not on directly perceived qualities nor on directly useful properties, but on the way in which certain things are causally related to other things, i.e., it denotes a relation. As chemical concepts become more and more those of relationships of interaction in constituting other substances, so physical concepts express more and more relations of operation: mathematical, as expressing functions of dependence and order of grouping; biological, relations of differentiation of descent, effected through adjustment of various environments, and so on through the sphere of sciences. In short, our conceptions attain a maximum of definite individuality and of generality or applicability in the degree to which they show how things depend upon one another or influence one another, instead of expressing the qualities that objects possess statistically. The idea of a system of scientific conceptions is to attain continuity, freedom, and flexibility of transition in passing from any fact and meaning to any other. This demand is met in the degree in which we lay hold of the dynamic ties that hold things together in a continuously changing process, a principle that states insight into mode of production or growth. End of chapter 9. Chapter 10: Concrete and Abstract Thinking. False notions of concrete and abstract. The maxim enjoined upon teachers to proceed from the concrete to the abstract is perhaps familiar rather than comprehended. Few who read and hear it gain a clear conception of the starting point, the concrete, of the nature of the goal, the abstract, and of the exact nature of the path to be traversed in going from one to the other. At times, the injunction is positively misunderstood, being taken to mean that education should advance from things to thought, as if any dealing with things in which thinking is not involved could possibly be educative. So understood, the maxim encourages mechanical routine or sensuous excitation at one end of the educational scale, the lower, and academic and unapplied learning at the upper end. Actually, all dealings with things, even the child's, is immersed in inferences. Things are clothed by the suggestions they arouse, and are significant as challenges to interpretation or as evidences to substantiate a belief. Nothing could be more unnatural than instruction in things without thought, in sense perceptions without judgments based upon them. And if the abstract to which we are to proceed denotes thought apart from things, the goal recommended is formal and empty, for effective thought always refers, more or less directly, to things. Direct and indirect understanding again. Yet the maxim has a meaning which, understood and supplemented, states the line of development of logical capacity. What is this signification? Concrete denotes a meaning definitely marked off from other meanings so that it is readily apprehended by itself. When we hear the words table, chair, stove, coat, we do not have to reflect in order to grasp what is meant. The terms convey meaning so directly that no effort at translating is needed. The meanings of some terms and things, however, are grasped only by first calling to mind more familiar things, and then tracing out connections between them and what we do not understand. Roughly speaking, the former kind of meanings is concrete, the latter abstract. What is familiar is mentally concrete. To one who is thoroughly at home in physics and chemistry, the notions of atom and molecule are fairly concrete. They are constantly used without involving any labor of thought in apprehending what they mean. But the layman and the beginner in science have first to remind themselves of things with which they already are well acquainted, and go through a process of slow translation. The terms atom and molecule losing, moreover, their hard-won meaning only too easily if familiar things, and the line of transition from them to the strange, drop out of mind. The same difference is illustrated by any technical terms. Coefficient and exponent in algebra, triangle and square in their geometric as distinct from their popular meanings, capital and value as used in political economy, and so on. Practical things are familiar. The difference, as noted, is purely relative to the intellectual progress of an individual. What is abstract at one period of growth is concrete at another, or even the contrary, as one finds that things supposed to be thoroughly familiar involve strange factors and unsolved problems. There is, nevertheless, a general line of cleavage which, deciding upon the whole what things fall within the limits of familiar acquaintance and what without, marks off the concrete and the abstract in a more permanent way. These limits are fixed mainly by the demands of practical life. Things such as sticks and stones, meat and potatoes, houses and trees, are such constant features of the environment of which we have to take account in order to live, that their important meanings are soon learnt, and indissolubly associated with objects. We are acquainted with a thing or it is familiar to us, when we have so much to do with it that its strange and unexpected corners are rubbed off. The necessities of social intercourse convey to adults alike concreteness upon such terms as taxes, elections, wages, the law, and so on. Things the meaning of which I personally do not take in directly, appliances of cook, carpenter, or weaver, for example, are nevertheless unhesitatingly classed as concrete, since they are so directly connected with our common social life. The theoretical, or strictly intellectual, is abstract. By contrast, the abstract is the theoretical, or that not intimately associated with practical concerns. The abstract thinker, the man of pure science, as he is sometimes called, deliberately abstracts from application in life. That is, he leaves practical uses out of account. This, however, is a merely negative statement. What remains when connections with use and application are excluded? Evidently, only what has to do with knowing considered as an end in itself. Many notions of science are abstract, not only because they cannot be understood without a long apprenticeship in the science, which is equally true of technical matters in the arts, but also because the whole content of their meaning has been framed for the sole purpose of facilitating further knowledge, inquiry, and speculation. When thinking is used as a means to some end, good or value beyond itself, it is concrete. When it is employed simply as a means to more thinking, it is abstract. To a theorist, an idea is adequate and self-contained just because it engages and rewards thought. To a medical practitioner, an engineer, an artist, a merchant, a politician, it is complete only when employed in the furthering of some interest in life. Health, wealth, beauty, goodness, success, or what you will. Contempt for theory. For the great majority of men under ordinary circumstances, the practical exigencies of life are almost, if not quite, coercive. Their main business is the proper conduct of their affairs. Whatever is of significance only as affording scope for thinking is pallid and remote, almost artificial. Hence the contempt felt by the practical and successful executive for the mere theorist. Hence his conviction that certain things may be all very well in theory, but that they will not do in practice. In general, the depreciatory way in which he uses the terms abstract, theoretical, and intellectual as distinct from intelligent. But theory is highly practical. This attitude is justified, of course, under certain conditions. But depreciation of theory does not contain the whole truth, as common or practical sense recognizes. There is such a thing, even from the common sense standpoint, as being too practical, as being so intent upon the immediately practical as not to see beyond the end of one's nose, or as to cut off the limb upon which one is sitting. The question is one of limits, of degrees and adjustments, rather than one of absolute separation. Truly practical men give their minds free play about a subject, without asking too closely at every point for the advantage to be gained. Exclusive preoccupation with matters of use and application so narrows the horizon as in the long run to defeat itself. It does not pay to tether one's thoughts to the post of use with too short a rope. Power in action requires some largeness and imaginativeness of vision. Men must at least have enough interest in thinking for the sake of thinking to escape the limits of routine and custom. Interest in knowledge for the sake of knowledge, in thinking for the sake of the free play of thought, is necessary then to the emancipation of practical life, to make it rich and progressive. We may now recur to the pedagogic maxim of going from the concrete to the abstract. Begin with the concrete means begin with practical manipulations. 1. Since the concrete denotes thinking applied to activities for the sake of dealing effectively with the difficulties that present themselves practically, beginning with the concrete signifies that we should at the outset make such of doing, especially make much in occupations that are not of a routine and mechanical kind and hence require intelligent selection and adaptation of means and materials. We do not follow the order of nature when we multiply mere sensations or accumulate physical objects. Instruction in number is not concrete merely because splints or beans or dots are employed, while whenever the use and bearing of number relations are clearly perceived, the number idea is concrete even if figures alone are used. Just what sort of symbol it is best to use at a given time, whether blocks or lines or figures, is entirely a matter of adjustment to the given case. If physical things used in teaching number or geography or anything else do not leave the mind illuminated with recognition of a meaning beyond themselves, the instruction that uses them is as abstract as that which doles out ready-made definitions and rules, for it distracts attention from ideas to mere physical excitations. Confusion of the concrete with the sensibly isolated. The conception that we have only to put before the senses particular physical objects in order to impress certain ideas upon the mind amounts almost to a superstition. The introduction of object lessons and sense training scored a distinct advance over the prior method of linguistic symbols, and this advance tended to blind educators to the fact that only a halfway step had been taken. Things and sensations develop the child, indeed, but only because he uses them in mastering his body and in the scheme of his activities. Appropriate continuous occupations or activities involve the use of natural materials, tools, modes of energy, and do it in a way that compels thinking as to what they mean, how they are related to one another, and to the realization of ends, while the mere isolated presentation of things remains barren and dead. A few generations ago, the great obstacle in the way of reform of primary education was belief in the almost magical efficacy of the symbols of language, including number, to produce mental training. At best, belief in the efficacy of objects just as objects blocks the way. As frequently happens, the better is an enemy of the best. Transfer of interest to intellectual matters. 2. The interest in results, in the successful carrying on of an activity, should be gradually transferred to study of objects, their properties, consequences, structures, causes, and effects. The adult, when at work in his life calling, is rarely free to devote time or energy beyond the necessities of his immediate action, to the study of what he deals with. The educative activities of childhood should be so arranged that direct interest in the activity and its outcome create a demand for attention to matters that have a more and more indirect and remote connection with the original activity. The direct interest in carpentering or shop work should yield organically and gradually an interest in geometric and mechanical problems. The interest in cooking should grow into an interest in chemical experimentation and in the physiology and hygiene of bodily growth. The making of pictures should pass to an interest in the technique of representation and the aesthetics of appreciation, and so on. This development is what the term go signifies in the maxim go from the concrete to the abstract. It represents the dynamic and truly educative factor of the process. Development of delight in the activity of thinking. 3. The outcome, the abstract, to which education is to proceed, is an interest in intellectual matters for their own sake, a delight in thinking for the sake of thinking. It is an old story that acts and processes, which at the outset are incidental to something else, develop and maintain an absorbing value of their own. So it is with thinking and with knowledge. At first incidental to results and adjustments beyond themselves, they attract more and more attention to themselves till they become ends, not means. Children engage, unconstrainedly and continually, in reflective inspection and testing for the sake of what they are interested in doing successfully. Habits of thinking thus generated may increase in volume and extent till they become of importance on their own account. Examples of the transition. The three instances cited in Chapter 6 represented an ascending cycle from the practical to the theoretical. Taking thought to keep a personal engagement is obviously of the concrete kind. Endeavoring to work out the meaning of a certain part of a boat is an instance of an intermediate kind. The reason for the existence and position of the pole is a practical reason, so that to the architect the problem was purely concrete, the maintenance of a certain system of action. But for the passenger on the boat, the problem was theoretical, more or less speculative. It made no difference to his reaching his destination whether he worked out the meaning of the pole. The third case, that of the appearance and movement of the bubbles, illustrates a strictly theoretical or abstract case. No overcoming of physical obstacles, no adjustment of external means to ends, is at stake. Curiosity, intellectual curiosity, is challenged by a seemingly anomalous occurrence, and thinking tries simply to account for an apparent exception in terms of recognized principles. Theoretical knowledge never the whole end. 1. Abstract thinking, it should be noted, represents an end, not the end. The power of sustained thinking on matters remote from direct use is an outgrowth of practical and immediate modes of thought, but not a substitute for them. The educational end is not the destruction of power to think so as to surmount obstacles and adjust means and ends. It is not its replacement by abstract reflection. Nor is theoretical thinking a higher type of thinking than practical. A person who has at command both types of thinking is of a higher order than he who possesses only one. Methods that in developing abstract intellectual abilities weakens habits of practical or concrete thinking fall as much short of the educational ideal as do the methods that in cultivating ability to plan, to invent, to arrange, to forecast, fail to secure some delight in thinking irrespective of practical consequences.
nor that most congenial to the majority of pupils. 2. Educators should also note the very great individual differences that exist. They should not try to force one pattern and model upon all. In many, probably the majority, the executive tendency, the habit of mind that thinks for purposes of conduct and achievement, not for the sake of knowing, remains dominant to the end. Engineers, lawyers, doctors, merchants are much more numerous in adult life than scholars, scientists, and philosophers, while education should strive to make men who, however prominent their professional interests and aims, partake of the spirit of the scholar, philosopher, and scientist. No good reason appears why education should esteem the one mental habit inherently superior to the other, and deliberately try to transform the type from practical to theoretical. Have not our schools, as already suggested, been one-sidedly devoted to the more abstract type of thinking, thus doing injustice to the majority of pupils? Has not the idea of a liberal and humane education tended too often in practice to the production of technical, but over specialized thinkers? Aim of education is a working balance. The aim of education should be to secure a balanced interaction of the two types of mental attitude, having sufficient regard to the disposition of the individual not to hamper and cripple whatever powers are naturally strong in him. The narrowness of individuals of strong concrete bent needs to be liberalized. Every opportunity that occurs within their practical activities for developing curiosity and susceptibility to intellectual problems should be seized. Violence is not done to natural disposition, but the latter is broadened. As regards the smaller number of those who have a taste for abstract, purely intellectual topics, pains should be taken to multiply opportunities and demands for the application of ideas, for translating symbolic truths into terms of social life and its ends. Every human being has both capabilities, and every individual will be more effective and happier if both powers are developed in easy and close interaction with each other.